Hello and welcome to another tutorial. This is tutorial number 2 of the GNSS Software Radio Toolbox for MATLAB. So in this tutorial I'll be talking about this state machine controller over here. But just to give you a quick context of the whole toolbox. So the way this works is all of the correlation functions for GPS baseband processing is implemented in C using multi-threaded processing. So these are the blocks that do all of that functionality, and this is implemented as a set of C libraries which are then brought into the MATLAB environment through this MEX interface over here. So the MEX interface allows you to work and do all of your algorithm development using the MATLAB environment. So the toolbox is distributed with this universal tracking loop that allows you to basically you acquire files, acquires GNSS signals, and then you hand those off um, to this GNSS signal configuration block, which then calls this universal tracking loop, and the correlations for the tracking loops are performed in C using multi-threaded processing. So now the universal tracking loop runs under the control of this state machine controllers, and that's the subject of this tutorial today. So before I get started, I want to say that all of the tracking loop implementations are based on the information that's in this book, Understanding GPS, Principles and Applications, 2nd edition by Kaplan and Hegarty, and specifically chapter 5. So all of the tracking loop implementations are exactly as how it's presented in chapter 5 of this book. Okay. All right. So now let's get into the MATLAB environment. And as we saw last time, the tracking is performed using this track GNSS track application right here. So same as last time, we are going to stay with the CA code tracking just to get started, and you set up your channel over here. So this is a single channel doing CA code tracking, PRN17, stream 1, and this one over here is the run set index. So basically that's the state machine state transition matrix that we are going to use to control the tracking loop. And so this RA1 is referring to a identifier that's stored in this file right here. It's runsets 2v06 and the date. So this file contains a whole lot of matrices, and each row is a state that the loop operates under, and then there are transition conditions to go from one state to another. So let me quickly go through this. So basically there is a state transition matrix for CA code. Then this one is for L2C. This is for L2C using CL and CM power combining. And then I believe this one is L5. Again, this one is L5 with power combining. This is L5 SBAS. Then this is for GLONASS L1 and L2 CA code tracking. This one is for Galileo E1 using narrowband functionality. So basically you are tracking the Galileo E1 signal as a BOC11. And same here with pilot and data combining. And then this is the Galileo E1 special modes of tracking. So this one implements several different modes to track up to full power, that is pilot and data combining with CBOC 61111 mode tracking, so that you're basically tracking the Galileo E1C the Galileo E1 signal with full bandwidth. And then this is for Galileo E5 A and B, and the same thing with power combining. And then L1 SBAS, and then I think finally Beidou signal tracking on B1I. So now let's go back to this first one, which is the CA code. And what I'm going to do is quickly make a copy of this so that I don't overwrite the original state machine. And I'll call this RA1T for temp. Okay. And then I'll go back here and call that state machine instead. And let's run this for starters. Let's run it for about 3 seconds. So let me set that up over here. And okay, so now let me explain what these states are. So as I said, each row is a state, and there are these columns that are defined over here. So the first column is the state type, and that's defined over here. So if the state type is 0, that's referred to as a normal state. And basically what that means is you set up tracking loop parameters, and usually you will jump out of that state by a given within a given time interval, or you can also jump out of that state given a certain transition condition. So we'll look at that later. State type number 1 is an acquisition state. And so this is the state that pulls in the acquisition parameters from the acquisition file that we ran. State type number 2 is a bit synchronization state. State number 3 is a overlay synchronization state. So what happens here is if you have a pilot signal that has an overlay code on top of the primary code, when this state is enabled, the tracking loop, what it does is it turns off the overlay code inside the code generator, and so as a result you see the overlay code in the signal, and then it attempts to synchronize the internal overlay code with the incoming code and finds the skew and basically synchronizes to that, finds the skew and synchronizes to the right skew, and then turns on the code generator's overlay code. And as a result, if everything goes smoothly, you will end up with the overlay code wiped off. So you will track the pilot without any data or symbol transitions after that. So once you have achieved overlay synchronization, you can typically go to a full POPLL tracking mode. So we'll talk about that later when we get to Galileo tracking. State type number 4 is a state that basically performs a code carrier divergence measurement and correction. So what this state does is, typically when you go from acquisition to tracking, there's a chance that you can lock on to one of the carrier Doppler side lobes. And when that happens, the way you know that this has happened is that the code and the carrier start to diverge. And so in this state, we measure that divergence over a given time interval, and then if the divergence is excessively high, we know that we have locked on to a side lobe. And if that's the case, this state will measure the divergence and perform a correction onto the carrier NCO. It will basically shift the carrier frequency so that the divergence goes away, and so you're locked on to the main lobe of the correlation functions carrier frequency domain, which basically is a sinc function. So you're at the top of you're at the main lobe of the sinc function when you're correctly locked onto the carrier. State type number 5 is called overlay sync 2, and this is a special case of overlay sync where there is a secondary code or an overlay code, and on top of that there's data symbols as well. So basically you have the primary code, the overlay code, and data on the same carrier component. And so in this case, we can't just find the overlay code. The search process is not as straightforward as in state type number 3 because there are symbols. So what this state does is very similar. It turns off the overlay code and then starts to search for overlay code patterns, both non-inverted and inverted, and basically tries to find them in the midst of the symbol transitions that are going on. So this state is applicable to the Beidou B1I modulation, which basically has the Newman-Hoffman 20-bit overlay code and 50 bit per second data message on top of that. So we'll talk more about that state when we get to Beidou tracking mode. Okay, so let me now quickly talk about this state transition matrix. So what it's doing here is the first state is acquisition, transfer, right? So we have that state type, and this K, it's a parameter that depends on the type, but in this case it's saying run this state for 500 milliseconds. And you can see a bunch of not a number or nan values in this matrix. So for the most part, what that means is ditto, that basically apply the same value as the value you see above it. Okay, so this is very easy to read, because when you see this, you know that when you have nans, you know that it's the same as the previous state, and these are the ones that changed, for example. Okay, so that's true for for this whole matrix except for these two over here. So when you have nans in these two columns, that means use the pre-detection and post-detection integration values that were used in the acquisition process. So basically this state is picking up the Doppler, the code offset, and the integration parameters that were used to find that signal, and applies those same integration parameters for the first stage of pull-in of the tracking loop. Okay, so now this column here is the carrier loop order. So number 2 means we would be running a second order PLL or a first order FLL or a frequency lock loop. This column here is giving you the bandwidth of the frequency lock loop. So we start here in this state with a FLL bandwidth of 10 Hertz. This column here is telling you the bandwidth of the PLL. So having a value of 0 means run this loop as a PO FLL only, so no PLL component in the tracking. Like I said before, this by changing these two, you are implementing a PLL FLL aided PLL architecture that's described in Phil Ward's chapter in the GNSS book that I showed you. This column is telling you the type of frequency discriminator algorithm that's applied for the frequency lock loop. By the way, this entire matrix, all of this stuff is defined in this file, the user call file, script file. And so this is a very long file. It's long because it has all of the different GNSS signal structures or the tracking parameters programmed onto this script. So in another tutorial, I will break this down and explain what all is going on in this file. But if I go to the top here, somewhere up here is the, okay, here we go. So this is showing you the frequency discriminator implementation. So you can see here that case number 1 means that we are implementing this frequency discriminator, and that's stored inside a function. So if we go to that function here, so right here, so it's basically taking I and Q, the current and the previous one, and the time between correlator dumps, and it's doing this A tan 2 implementation. So this is the implementation that's described in the Kaplan book in Phil Ward's chapter. Okay, so back to the state machine here. Incidentally, you saw that having a value of 0 means that the frequency discriminator output is set to 0. Okay, and so what this means is that we basically turn off the frequency discriminator, and as a result we can save some computations because we are not doing this arctangent operation over here. Yeah, so down here we turn off the discriminator. But up here we are using the frequency discriminator type 1 with 10 Hertz bandwidth, and here you can see the bandwidth is stepped to 0 and then back to 5 again. We'll explain that later. Here is the phase discriminator type. So similar to this one, 1 means that we are doing a costless PLL, and if we set that to 2, we are doing a POPLL 4-quadrant arctangent discriminator. So obviously, because this is CA code and there's data riding on the signal, we can't implement a POPLL, so it has to be costless. So all throughout it's a costless PLL. This column is showing you the order of the code tracking loop. So you could set that to be first order, second order, or third order. But in this and in most of these, pretty much all of these matrices, it's set to order number 1. And that's because we are doing carrier aiding. So when you do carrier aiding, all of your dynamics are tracked by your carrier tracking loop, and all that the code tracking loop has to do is account for code carrier divergence. For example, due to multipath or ionosphere. So because aiding is turned on, we implement a first order code tracking loop. This column here, BD, is the bandwidth of the delay lock loop that's doing the code tracking. So we start off with a bandwidth of 10 Hertz. Okay, this column here is the spacing between the early and the late correlator points. And you can see that we start off with 1 chip correlator spacing, eventually go to 0.5, 0.25, 0.1, and eventually we settle on a very narrow correlator spacing of 0.01 chips, early minus late. This DDC column is the identifier for the code discriminator. So very similar to the frequency discriminator, the code discriminator, there are several types that are programmed in, and so we are using 3, 8, and 114. So let's quickly have a look at what those are. So let's go to 114, and so you can see here in this user call is where all of these discriminators are programmed. So 3 is doing a envelope early minus late divided by prompt implementation. Okay, so that's implemented as follows. So it's 0.25 times early minus late divided by the prompt. Then the next one we had was 8. Okay, so 8 is a I-coherent early minus late divided by prompt. So here we are not taking the envelope of I and Q, but rather we are only taking the I channel because we are operating the code discriminator as a coherent, and this can only be done when the carrier tracking loop is running as a PLL in phase track mode. Then we also implement 114, and so 114 happens to be the I-coherent double delta HRC, which is the high resolution correlator. So this correlator has 5 points, and so you have a prompt, and then on either side the inner 2 correlators on either side of the prompt is implemented here, and then the outer pair is implemented here, and then finally the HRC double delta is implemented as D1 minus 0.5 times D2. All right. So okay, and then this column here, UMod, is a user mode that we use to combine correlator outputs for carrier tracking as well as code tracking. So that's not used here, and so when it's not used, we use user mode 0. Okay, this column TNS is the transition to next state, and so with this we can actually control very elaborate transitions between different states, but here it's going sequentially downward. So having a value of nan basically says go from this state, when you do transition to the state that's immediately below it, and so forth. So it's basically going to step just how this is written. But if we were to, like, say, over here set this to 1, then when this state transitions, it will go back to state number 1. All right. This column here is doing a PLL phase lock threshold based transition. So actually in this toolbox version, this is the only transition that is controlled by a tracking indicator. So what's happening there is that when the phase lock indicator achieves a threshold of 0.9, then it gets armed to transition to the next state. So that's this state over here. Oh, actually, yeah. And the next state for that is programmed over here in this column. So when it does transition, it transitions to the state that's the next state, because this value is nan. If we had, for example, set this to 3, then it would go from here. If this condition is met, it will go to this state. All right, and then the final column here is measurement reset. So what this does is, if there is a 1 in this state, in this column, then the pseudo range and the carrier phase values that are being computed are reset back to 0. So this helps us to look at code minus carrier with a offset of 0. So typically you do this after the entire tracking loop has settled on the final state that you want to do your steady state tracking, and you set this to 1 to reset the measurements back to 0, and then that will allow you to see code minus carrier with respect to 0. Okay, so I think this pretty much covers this tutorial. In the next one, I will continue with this state machine and explain what all is going on in this. And then what we will do is kind of interrupt this process and have a look at some of the intermediate tracking states. All right, thanks for listening, and see you next time.